Hey everyone, I'm about to Google Kickstart. This is round B of 2021, and unfortunately, I forgot about it until just now, and so I'm starting 7 minutes late. But we'll just give it a go and see how we can do. I might as well do this. Increasing strings. Substring ends at position I. Oh, you just see how long you can go back. Okay, so sure. Oh, that's right, that's not the right template. Why isn't there a template here? I guess I want the cogem template, right? Okay, that's what we want, yeah. Say if si minus 1 is, then longest I is longest I times 1 plus 1. And we'll just output this vector. And it looks good, so we can just submit it. Okay. I see. Okay, so it's like okay, so we should take the consecutive difference array, and then everything except for 2 consecutives. Oh, but the 2 consecutive have to add up to. they're all the same. They're all the same except the last one with the first one. And then they're all the same except for 2 consecutive, which add up to. If so there's also okay, this is good. Did you get this? Okay, I got this. Okay, I got this. Alright, which bits are here? Let's give primes. To the 18th. I see. Okay, so this should be easy with the Miller or int Miller Raven. Cool, and then we're just gonna read C. Cool, and then truck delivery. A lot of weight, no W in city C and also city unique cities. What? From okay, so it's a tree. You go from 1 to C. Okay, so okay. Wait, so yeah, so basically we take we can sort the queries by weight, and then when the weight increases, we start including these. These secretary on these. Is that what we want to do here? I guess so. Okay, let's do it. How does it start? N and Q, okay. Okay, and then city, weight, and index. We can sort it by weight. And then we're gonna have basically we're gonna have a lazy seg tree. No, here's the tree, sure, whatever. It just has one thing, to GCD, which defaults to 0. Okay, and then okay, so now we're gonna have a tree. Everything starts at 0. Everything starts at 0. Here's what we're gonna do. As the weight increases, the load okay, let me activate that. Yeah, so like yeah, this is limit, not weight. And then what we're going to do is tree.update our start node. Everything in this tree is going to be plus plus answers is going to be tree.query tree.city All right, let's do it. Did I int 64 everything that needs to be int 64? Charge is int 64. This is 64 int 64. Yes, we did it. Oh my god. Started 7 minutes late. Still beat everyone. Oh, that was very lucky. Was not expecting that to happen, but Okay, nice. Oh man, I actually almost forgot about this. Showed up just in time. Okay, it's about halfway into the contest now, and yeah, that was pretty crazy. I started 7 minutes late, and I knew I had to make up for some lost time, so I basically um, tried out some things to basically aim to make up for that lost time, and everything just went really well. I think I solved every problem on first compile, so I didn't have to do any debugging. But yeah, basically what I'm going to do now is I'll explain my thought process and my solutions for each of these problems, and probably grab a bite to eat after that. So let's just jump into the first problem. So the first problem is increasing substring, and basically we have this definition. A string is called strictly increasing if any earlier character is smaller than any later character. So ABC is strictly increasing, and ADF is also strictly increasing. But ACC is not. This has two equal characters in a row, so it really has to be strictly smaller. And then FTA is not. It's actually the complete opposite. It's decreasing. But the only thing that matters in this problem is increasing. And so in this problem, we're asked basically for every position, what's the length of the longest strictly increasing substring that ends at this position? And in the worst case, n is up to 2 times 10 to the fifth for the second test set. So we need to do something faster than quadratic. And basically the main idea for this problem is, of course, we can always get a string of length at least 1 because we can just use the single character itself. And then we can think about just going left from our ending point and seeing how far we can go before we basically have a comparison in the wrong direction. So from C, we can go to B because that's in the right direction, it's increasing from B to C. But then we cannot take this extra beat because that would make 2 equal characters. And like a similar story from here, from this C, we can take this A, but we can't take this B because then B and A compare the wrong way. B is bigger than A. So one thing we could do is we actually could just start from every position and just go backwards until it's bad. The reason that that's fine is because we can only go at most 26 times because we only have uppercase English letters. But we can even do better than that. Basically, the longest at I, if si minus 1 is less than si, then the longest at I is just the longest at I minus 1 plus 1. And otherwise it's 1. So basically this array is initialized to 1. For 0, it's always 1. In fact, we don't even need this because it's already set up here. And then, yeah, we just go from left to right and solve this kind of like a greedy approach here. And so that gets us the answer. So pretty simple problem here. Now for the second problem, longest progression. So basically they define an arithmetic array, which is basically just an arithmetic sequence. So some examples, 9, 10, 3, 3, 3, or 9, 7, 5, 3. And so keep in mind that the sequence can go down. So here the difference between every consecutive pair is -2. And so that's still good. And we have an array A. It has n non-negative integers. N is up to 3 times 10 to the fifth in the worst case. And we need to replace, or we're allowed to replace at most one element of the array with any integer we want. And then we want to figure out what's the longest possible arithmetic subarray if we are allowed to replace at most one element. So for this problem, what I did was I looked at these consecutive differences. So again, for this array, the consecutive differences would just be -2, -2, -2. Notice that we have one less value when we take the differences, and that's normal. And the reason that's better is because it makes it way easier to tell if something is an arithmetic array. It's just all of the differences have to be equal. And then if we're thinking about replacing one element of A, then essentially if we start from a subarray of A, so let's take, let's take some subarray of A. So maybe we'll have like, okay, and then let's say, maybe I'll mess up this value. So let's take this subarray, and we want to know if we can change one element and make it into an arithmetic array. Well, there's kind of two different options. One is that we change either the first element or the last element. When we do that, essentially, if we look at the differences, is that the right number? One more. Okay. So essentially, if we look at the differences, then if we change this to 2, right, then we're just essentially changing that first difference and nothing else. And the case for changing the last element is very similar. We're just changing the last difference and nothing else. The main difference is if we change something in the middle. So now if we imagine let's say this 12, instead of being a 12, let's say it was a 19, right? So now the differences look like 4 minus 2 is 2, and so on. And then once we get to 19 minus 10, then we have 9, and we have negative 5, 2, 2. And so when we change this 19 to a 12, we're actually changing this 9 and negative 5 into 2, 2. And then we're good. So the goal, as always, is to, let's see. Am I missing a value here? I think, okay, I guess it's not super important. I had too many values here. Yeah, okay. There we go. So yeah, basically what we can do is we can take two differences that are right next to each other in our list and replace them with our desired difference if the sum stays the same, right? So 9 and negative 5, they sum to 4, and then this is why 2 and 2 works. If it were, for example, 9 and negative 6, then we would have 13 here, 15, 17, then we wouldn't be good, right? So it only works because these two values that are wrong sum up to 2 plus 2. And so those are kind of the two cases involved here. One is changing the end and one is changing the middle. So yeah, basically to do that, I took the array, I calculated the differences, and then I do this thing where I solve D. I have this function called solve, I call it on D, then I reverse D and I do it again. And that way it helps reduce some of the casework. So I don't have to consider both first and last. I can just do, I think I did just last. And then this middle thing is also something that I consider. And it also helps kind of the cases where, for example, the left side doesn't exist or the right side doesn't exist. Like the right half, the left half of the 2's doesn't exist or the right half of the 2's doesn't exist. And yeah, and so this solution, this function, it's basically just, I do a loop over the kind of equal ranges of the D array. And so in this loop, I to j is like a maximal equal range of the D array. And so one choice is just to take all those equal values. If j is not the end, then we can include the value after because of this idea, basically. And then this check gets us this case, right? So if dj plus 1 is equal to 2 times di, then we have this case that we want. And then we can see how many more 2's are afterward, or in this case di, how many more of di are afterward. And so we keep pushing back and counting the di. And then that gives us another possibility. And even though this loop looks a bit tricky, it's actually O of n because j only goes up in the entire loop. And so it can only go from 0 to n. And then this n thing, this is a little bit trickier, but basically if we have a very long, if we have this case where we have 9, negative 5, then we have a ton of 2's afterward. we can spend a lot of time counting these 2's, but that will only happen once for this range of 2's, which is exactly for the range of 2's before that. And so it's more like basically 2n iterations that we have to worry about. So that's problem B. This was a tricky one. It helped definitely to think about the different cases and work out the details. And then the reverse kind of trick here also helped make it simpler to code, where we don't have to worry about these corner cases as much. Basically, you just handle one of them, which is, in my case, I handled this one. And then this one is handled for you when you reverse. Okay, so 2 more problems to talk about. This one is consecutive primes. So basically, we take these prime numbers, 2, 3, 5, 7, 11, and so on, and we're given a value z. We want to find the secret code, and the secret code, we're told that it's the largest product of 2 consecutive prime numbers that is smaller than or equal to z. So I think one example I had for 2021, the secret code is exactly 2021 because 43 times 47 is 2021, and those are 2 consecutive primes. There are no primes in between. For 2020, then we have to do 1763 because that is 41 times 43, and that is the largest we can do because we just saw that 43 times 41 is too big. The tricky thing here is, in the worst case, z is up to 10 to the 18th power, and we have to solve 100 tests in 15 seconds. So for this problem, I basically just use binary search, where I kind of like start with a particular method to find a prime. So this method basically does, given n, find the smallest prime that is at least n. And my binary search is essentially finding what is the biggest number, let's say x, where the next prime starting from x times the next prime after that is less than or equal to z. And that's my binary search. And so this is what the evaluate does. It finds the next prime starting from x, and then finds the next, which is p, and then finds the next prime starting from p plus 1, which is just the next one after that, and then returns p times q. And so that's how I do the binary search. Basically, this here, low and high, we just start with the range 0 to basically 1.1e9. I just did that to make it a little bit bigger than 1e9, just in case. Although actually, yeah, we don't need that. 1e9 would have been fine here. But yeah, just run a binary search, and then you just evaluate the result of the binary search. And in my case, I used Miller-Rabin with kind of some special witness values that work for any value up to 2 to the 32. So this is a pretty fast, pretty fast primality testing algorithm for any number up to 2 to the 32. And yeah, so this should run super fast. It's like essentially log of 1e9 times, this is kind of like log, kind of like constant time, depending on how you look at it, but also super fast. So it's kind of like a log squared is like the worst case you can think about it. You can also be a little more clever and just find the closest primes, find a couple of the closest primes near the square root of z, and that way you don't have to do a binary search. You can just check like O of 1 different prime candidates. Maybe like, I think you probably just want to check, yeah, like 2 below and then 1 above, something like that. But that probably involves a bit more casework. The binary search was really easy to code and like didn't have any of these concerns about like off by ones or things like that. And yeah, so that was kind of part of what I was going for here. It was just the first thing that I thought of that seemed straightforward enough to code, and so I just went for that. And yeah, that definitely paid off here because this third problem was the fastest problem for me by a lot relative to like how much time most people spend on the problem. And I think after the third problem, I was in third place at that point. And so I knew I had some, basically Steven was in first place and Andrew was in second place, I believe. And so I know both of those guys. And yeah, I knew I just had to make up some ground on the last problem. So we can talk about that one. In this problem, we've got a tree. The tree's called Google Land. And it's got n nodes. Each node is a city, and each edge is a road between two cities. The capital is city 1. And every day, Charles picks up a load which has a weight of W and starts in city C. And he wants to deliver it to city 1 using the simple path between C and 1. So if you route the tree at 1, basically you're just going straight up to 1. And then we're told that each road I has a toll. So it charges an amount AI if the weight of the load, if W, is greater than or equal to the limit Li. And Charles works for Q days. Each day he's given the starting city C and the weight of the load W. And we need to find the greatest common divisor of all of the toll charges that Charles pays for that day. So on his way from C all the way up to 1, what is the GCD of all of the charges that he has to pay? And I don't know why it's GCD. In the story, at least, it doesn't seem like it makes any sense, but it turns out to be, a nice, solvable enough problem with that. But basically, this is a pretty standard tree query problem. The main idea is actually that it's a couple things. The first thing is that you don't have to solve all the queries in order. That makes things simpler. You can sort the queries by their weight. And so that way you can do a sweep of the edges or the roads by their limit as you're going through the queries. And then another thing that's helpful here is to use the pre-order traversal of the tree. I guess this particular article is talking about binary trees, but essentially it's just the DFS order of the tree. And using this, the nice thing about it is it lets you express a subtree of the tree as just a range of an array instead. So yeah, those are the main things we'll be using here. And then we'll throw in basically a seg tree on the GCDs here, and that will let us perform these queries. So essentially when we want to activate an edge, we have a subtree underneath that edge, and all of those nodes get affected. So we just have a contiguous range of an array, which is the pre-order or traversal array. A contiguous range of that array gets affected by that GCD, and so that's why we can do things with the seg tree. So for the actual code itself, basically, used a couple different pieces of pre-written code. One is to kind of handle trees in general, and then brought in some. This is the seg tree code, and so a bunch of different things going on here. But the main thing here is just the sweep and tree idea here. So first of all, made a couple structs. One is for the edges, one is for the queries, and made them both sortable. So edges are sortable by limit, queries are sortable by weight, or comparable by weight. Yeah, so you just start with reading the edges, building the tree structure, and this also gives us the pre-order for the tree. Now we're going to sort the edges by sort them by their limits, and then we're also going to read all the queries and sort the queries by their weights. And we're going to just save the answers for each query here. And now the key thing is, yeah, as we're going through the queries, because the weights of the queries are increasing, basically the list of edges that will actually charge, or the set of edges that will actually charge, is also just strictly increasing. Or maybe, I guess, non-strictly increasing. And we can just apply those one by one as they become relevant. So an edge becomes relevant once its limit is less than or equal to the current query's weight. And once that's the case, we just need to kind of figure out what is the subtree that's affected. So first we figure out since we have the edge that's like x to y, or it might be y to x, we just figure out which one of the two is lower. which is the one with the greater depth. And then we update, like I said, the subtree range. So that's the tor start to the tor end of that node. And we update it with that charge. And then finally, the answer for this query is just going to be the GC value in our seg tree at the particular city. And yeah, that's it. So overall, a pretty long file, but most of the code that we had to write here for this was just in this little area. There's a little bit of like customizing the seg tree as well here, but nothing too crazy. Yeah, so those are all of the solutions for today. Thanks for coming and checking out my video, and yeah, check out the rest of my channel for more competitive programming and other just problem solving and algorithms videos. And I'll see you in the next one.